University of Malaya, and Professor Dr. Peck from the Department of Software Engineering, Faculty of Computer Science and Information Technology, University of Malaya. Thank you, and please be seated. Assalamualaikum warahmatullahi wabarakatuh, and good afternoon. Professor Dr. Shaliza Ibrahim, Associate Vice Chancellor, Research and Innovation, University of Malaya. Professor Dr. Abriza Abdullah, Dean of Faculty of Computer Science and Information Technology, University of Malaya. Professor Dr. Peck, Department of Software Engineering, Faculty of Computer Science and Information Technology, University of Malaya. Management of Faculty of Computer Science and Information Technology, University of Malaya. Distinguished guests, and ladies and gentlemen, welcome to the inaugural lecture by Professor Dr. Peck from the Department of Software Engineering, Faculty of Computer Science and Information Technology, University of Malaya. Today, Prof. Lee is going to deliver her lecture entitled Traversal of a Software Engineering Research Landscape. So without further delay, I would like to invite Professor Dr. Shaliza Ibrahim to chair the lecture and introduce Professor Dr. Peck.
Terima kasih Puan Pengerusi Majlis. Yang berusaha Profesor Dr. Abrizah Abdullah, Dekan Fakulti Sains Komputer dan Teknologi Maklumat. Timbalan-timbalan Dekan, Ketua-Ketua Jabatan, tuan-tuan dan puan-puan sekalian, Assalamualaikum warahmatullahi wabarakatuh dan salam sejahtera diucapkan kepada semua hadirin yang dihormati sekalian. Bagi pihak Universiti Malaya, saya mengalu-ngalukan kehadiran tuan-puan dan amat gembira berada bersama di Fakulti Sains Komputer dan Teknologi Maklumat sempena syarahan Perdana Profesor Dr. Peck sebagai Profesor di Universiti Malaya. Izinkan saya untuk meneruskan dalam bahasa Inggeris. Ladies and gentlemen, honoured guests, it gives me great pleasure to extend to all of you a very warm welcome. It is indeed an honour for me, on behalf of the University of Malaya, to be able to chair this afternoon's inaugural lecture by Professor Dr. Peck, a professor at the University of Malaya. To quote an ancient proverb, if you are planning for a year, sow rice. If you are planning for a decade, plant trees. And if you are planning for a lifetime, educate people. Today we celebrate an educator, a professor at the University of Malaya. Please allow me to introduce Professor Peck. Professor Lee has been working at the Faculty of Computer Science and Information Technology, University of Malaya since November 1994. She obtained her Bachelor of Science in Computer Science from National University of Malaysia, Master of Computer Science from University of Malaya, her Diplôme d'études approfondies DEA in Computer Science from University Pierre Marie Curie, and her PhD degree in Computer Science from University Panthéon-Sorbonne or Paris 1. Her current research interests in software engineering include object-oriented methods and case tools, software reuse and application framework, requirements and design engineering, software clustering and traceability, and software fault localization and prediction. Professor Lee has published an academic book, a number of book chapters, and more than 100 papers in various local and international conferences and journals. She has been an active member in the review and program committees of several local and international conferences and was a panel member of the National Accreditation Board for several years. She is a member of IEEE Computer Society and was a founding member of Informing Science Institute and the editorial board of University of Malaya's Research Bulletin in her early academic career. She has served as the executive editor of Malaysian Journal of Computer Science for several years and is currently the editor-in-chief. In addition, she was an invited professor at Information and Communication University, South Korea from 2005 to 2006 and at the University of Paris 1, Panthéon-Sorbonne, France in 2012. Professor Lee is currently a principal investigator and co-investigator of a few national projects funded by FRGS, PRGS grants, and in the past has been principal investigator of national research projects funded by IRPA, Science Fund, and the University's Short-Term Fund. She has also served as technical consultant in industrial projects on several occasions. She is currently the experts referee panel of Kuwait University for research review and evaluation of scientific projects received for funding support, and was an expert review panel member of Academy of Sciences Malaysia for a few years. Currently, Professor Lee Peck is supervising over 10 postgraduate students and has completely supervised and graduated 13 PhD and 38 master's students. Over the years, she has received several outstanding service awards and had won several medals on her research in local and international intervention and innovation exhibitions. With that brief introduction, I would like to invite Professor Lee Peck to present her lecture entitled Traversal of a Software Engineering Research Landscape.
Thank you, Prof. Shaliza. Thank you to all for coming to my lectures, Professor, Doctor, and all students. Okay, the title of my lecture today is Traversal of a Software Engineering Research Landscape. So I'll briefly present to you the research studies that I've conducted since I joined the faculty as academic staff. Okay. First of all, I would like to acknowledge and thank the following people for being my link of support, whether in my life or in my career. My parents for their great sacrifice and unconditional love. My siblings for their love, constant support and encouragement. University of Malaya, where I acquire valuable knowledge and where I built my academic career. The Vice Chancellor, University of Malaya, Dato Abdul Rahim. The Dean, Professor Dr. Aprisa, and management team of FSKTM, and all the staff who have spent their time planning and also planning for this lecture session. My dear colleagues and also department members who have been very kind, giving kind support and cooperation during my career here. Okay, my students in the lab who have been dedicated and committed in their career and also sharing of research ideas. So briefly, the content of my presentation is as follows. Basically, started from the early phases, second phase of research landscape, and third phase. So basically, the research landscape is divided into three. Okay. So I started my academic career at the Faculty of Computer Science in 1994, November. After finishing my PhD at the University of Pontianak, Sorbonne. So at the time, I slowly built my academic career. So my research activities has been supported by a mix of research fund. As you can see in the early phase, we had the fund, both F, UPA. UPA is one of the grants in the 1920s, 19th and 20s. And the later part, we have eScience, FRGS, and PRGS. I have also been involved in a few consulting projects with the private companies during my early career. And also during my early career, my research actually was inspired from the ideas from the industrial project, one of the industrial projects. So this is a glimpse of my research landscape. As you can see, it revolves around the main areas of software engineering in the software lifecycle, such as requirements engineering, design engineering, a little bit of testing, and maintenance issues. So the research study at the different phases are related to the topic of object-oriented method and to case 2 development, software reuse and framework development, UML model changes, and also transformation, okay, software quality in the architectural design, software clustering and traceability, representing OO software using complex network. Also a little bit of testing, which is related to the test strip reduction. So my early phase of research landscape started from November 1994 to 2005. So the first early phase is to solve two main problems of software engineering. That means the need to have a means to represent real-world systems that is closer to the user point of view. So at that time, techniques from the traditional methods such as functional decomposition method and structure method was used. But these methods, they provide a concept said to be not closer to the user point of view in the terms of modeling. And also these techniques, they suffer in terms of the impedance mismatch in the sense that there is a need to transform concept from the high level to the low level, such as from analysis to design. If we have an analysis model, it needs a great transformation due to the incompetence concepts. Okay, so all this problem that led to the evolution of object-oriented language. So at that time, object-oriented programming was popular, but not the high level, such as the analysis and design. So there was a need to come up with techniques that can actually allow developers to model high-level view of the software that is closer to the user point of view. And the approach taken is so much related to object-oriented method and also techniques, providing techniques that allows the developer to model the different aspects of a software system in terms of structural, behavioral, dynamic aspects, so that everything can be captured at the high level view. Okay, so the other problem is related to the need to speed up software delivery. It was said that it took a long time to deliver a software, but to actually have a dramatic improvement in the software delivery, you need to capture the last structure of the software, not at the function level. So reuse is one thing. At that time, people started to use reuse, but actually at the programming level. They actually reuse. It's a small reuse at the function level. At that time, what we want is to reuse the last structure. That means the whole infrastructure of an application domain. And that is why we opt to the approach of software reuse, specifically on object-oriented framework. Okay. So this is about the approach taken to define techniques, methods that can actually allow developer to model software systems that is closer to the user point of view in terms of structure and behavior. Okay, we perceive a system, a real-world system, having different views, structural, behavioral, and dynamic aspects, and all these have to be captured completely, consistently. Otherwise, you will not be able to develop software that is complete and consistent. Okay, so in this sense, we actually define the method, OO method, that is for the analysis method. Okay, and then supported by set techniques that allows to model the different aspects of a software system in terms of structure, behavior, and the dynamic aspects. Okay. And in that sense, we actually wanted, in order to have a view that is closer to the real world, to the user point of view, there is a need to support visual modeling. So for visual modeling, it needs a set of high-level notations. Okay. And for this particular approach, we follow through to the development of case 2. Second problem, as I said just now, we went to the approach of defining object-oriented framework, but we want to target at the application domain. Okay, so a framework is actually captures the infrastructure of an application domain, the common functionality. Okay, it's a reusable system that captures the common functionality of a software, and on top of it, this common functionality, it has been defined with a variability, which means that variability point. On top of this point, we can customize. So we need to know software reuse principle. We need to define what are the customization techniques to be supported at each point. It is at each point that the developer can actually customize when they reuse. That means they will not be develop software from scratch. That means from nothing. They will have to reuse from the framework and just customize from the points, different points. So the difficult job is to identify components that is actually reusable. And not only the common components, we also need to define the differences. Okay, differences so that the developer can actually customize. Okay, so I go to the first approach first. The first approach, object-oriented techniques, okay, it has been supported by an OO modeling conceptual model with a set of well-defined concepts. Okay, in order to capture things from the real-world system, we need a set of a concept rich enough to be able to capture every aspect. So it has to be well-defined. It means semantically, it has to be defined well. Okay, and also it should be supported by a graphical representation. So in this case, we give notation. Okay, each concept is related to every notation. So in that case, it is said to be semi-formal. At the same time, formal, but also semi-formal. Okay, so all these visual modeling tools, they are semi-formal. In the sense that they give notation that is formal enough, but at the detail part is actually not so formal. Okay, so all these concepts will be able to support or to model the different aspects, statics aspects, dynamic aspects, and behavioral aspects. Okay, to capture all those different aspects of the software system. On top of that, the method is also supported by a set of methodological guidelines. The guideline that it will guide developer on going about how to define their model. Okay, their model of a software system. Okay, a real-world system is actually represented by a model. Okay, it's a representation. It's just a representation. Okay, a model of your software system. Okay, the method is also supported by a set of rules, consistency and verification rules. This is when we build the tool, we can build the rules for consistency, checking consistency. When the developer model the tool, the model, then there is built-in consistency checking rule that will check when the developer model. If there's any inconsistency, it could report to the developer. Okay, verification rule, also the same thing. Okay, other than that, we also look at the quality aspects. The quality aspects in analyzing see the focus of syntax, semantical richness. So a model that is rich enough will be able to capture all aspects of a real-world system. So the set of concepts have to be rich. Okay. So finally, we automate it. Okay, that means we automate it into a case 2 that we call as a workbench that allows, okay, designer or developer to use it, okay, to model, okay, at the requirements analysis level, okay, requirements analysis level at a very high level. We built the tool based on a very primitive version of C++. At that time, in 1990s, 20s, we could only afford to get a very primitive version. It has only a set of very basic classes library that we could use to build our tool. We do not have the luxury like nowadays. You have a very very advanced Visual C++, where they are built with a lot of all these frameworks, OO frameworks, where you can build your GUI very easily. And then to build an GUI, we actually spend a lot of time even to come out with a notation. Okay, so even now, the OO framework in the visual paradigm, what do you call it, in the visual paradigm is a case 2, okay? Visual C++. Okay, in Visual C++, there are a set of OO framework. It's actually built using this MFC. So it's a layer up to facilitate the developer in developing their application. Okay, so we managed to come up with these tools. So all these are hard-coded, okay, to capture the structural view of a software system in terms of classes, relationship, association, and so on. Okay, and also the dynamic aspects, okay, how the objects interact among themselves. Okay, right, and also the behavioral aspects in terms of event happen. When a certain event happen, it could trigger certain operation to lead to the change in the software system. Okay, so we managed to capture all these different aspects, okay, at that time. Okay, to think about it, UML is another modeling language that now is a de facto standard for object-oriented modeling and design. It was first defined in 1996. First version came out in 1996. Now, of course, we have higher version. Okay, so UML come out with a meta specification, okay, meta model. Okay, that was hard coding to case 2 development. Actually, there is another approach to develop case 2, which is a faster way. Okay, by using meta modeling. Meta modeling. Okay, for that we need a meta case. There is a case, and there is also meta case. Meta case basically is a case for a case. That means you can automate your method, automate into a case 2 by using a meta case. The meta case itself is supported by a meta model. So by using the meta model of the meta case, the one that we use is actually meta edit. Okay. By using the model, the meta model of the meta case 2, we have to define our concepts. We define our concept by using meta model of meta edit. What we need to do is just to define using their meta model. Then this case 2 has a compiler. You compile your model, check everything is correct and so on. And after that, if it's correct, it will create a case 2 for you. So this is a very fast way of developing a case 2. But the problem is that you have to depend on the case 2. Okay, that is the problem. So the meta model is called OPRR, Object Property Role and Relationship. Okay. It is actually based on the 4-layer meta model architecture or model-driven development. So we are at this level. If you define your tool, UML is at this level. ER, DFD, all are at this level, third layer. Okay, so with this model that you have, developer can use it to model their system. They are at this level. The instances are here, but we use the meta model to model our tool to come out with a case tool. Okay, so this is the 4-layer meta model architecture. Okay. Okay, so we are here. Okay, here, and the developer can use it to model their system. Okay, and if you use meta case, okay, you have to rely on their notation. So you cannot, it speaks for you. You can say you can still select some that you want, but within the limit. Okay, so you cannot say very free that I want this notation and that. Okay, it's limited by the tool. Okay. So the second problem is go to the approach of O framework design. A framework is basically a reusable system, a generic structure that captures the whole application logic of a certain application domain. Okay, your domain itself. Of course, you can have developed many systems inside the domain, but you only capture the whole domain. It doesn't focus on individual application, only the domain of certain, like for example, banking domain. So why? Because you need to do a domain analysis to actually identify common components within the different banking applications. And all this you want to put into the framework as the generic infrastructure. So all these components are related. Okay, common components are related. But in order to be able to customize, we have to define places on top of this framework, on top of this general functionality, the points where you can exploit for differences. Because ATM in one bank is slightly different from ATM from another bank in many aspects, in terms of layout, UI, in terms of reporting. This could be different. So all these differences, you still need to plan in the framework so that the framework can make it available for the developers to select, because our purpose is to speed up the development of a framework. So if they can select, then that is even good. If it's not available at that point when you customize, then they can integrate the code, but it's only a small code that they integrate. Okay, so a framework is a generic infrastructure. Okay, so it actually depends on an application domain. Okay. So for that, variability point is actually the point where you want to incorporate customization technique, certain customization. Different point, you have different customization technique. These are the points when the developer reuse, they customize at these points. Okay, they customize at this point. Windows, they use also this customization called widget. Okay. That is a place where you, for example, when you install, then you can install for work environment, for your home environment. So basically, the system asks you in question, but you don't see. Okay, so you just provide the answers and customize. Okay, so it's on customization technique. So we managed to build two frameworks. One is on the application domain, and the other one is on persistence. See, persistence is linked to connection to the database, provide services for database query, database creation, deletion, and update. Okay, so these are the services. You will see all the databases, they have the same services. Okay, so a framework can support many databases. You can connect to many. Okay, that means it actually support many. Okay, so in this case, we try to support 3. Okay, support one multi-dimensional database, one relational database, and the other one is XML. Okay. So we built the application framework, okay, with all these production planning, scheduling, inventory control, and process control component. Okay. On top of that, we built an IDE where the developer can customize and also can develop their form or screen design. Okay, so this framework is called EMF, okay, Manufacturer Application Framework with IDE. So this is the architecture. Basically, the whole framework is divided into component system. A component system actually captures components, a set of components interrelated, okay, on a certain aspects of the application domain. So you have the 4 layers: application layer, business layer, you have the middleware layer. So that's why Visual C++ it has a framework basically supporting the middleware layer. Okay, middleware layer. Okay, graphic. Okay, and then the system layer. So we are involved in these two because ours is high. We want to put it as an application domain, reusing the big structure of an application. Okay, so if you see it like that, you know, if somebody wants, a developer who wants to develop an application system, they can just import some of these components from the component system and they customize it and develop. That means they have to develop using the framework, okay, components. Okay, so this is another view. And these are the two, IDE we have developed. Okay, all these developer view, they can look at the components, the set of components, then they can select one and customize. Okay, they can create their form. We also develop a component for GUI that they can, once the developer can design their form, then the code will be generated, automatically generated. We use Java, okay, to do that. You can see that after selecting, customizing, then the code is generated, okay, Java code. Okay, this is the end user view. You can customize without adaptation, you can reuse a framework without adaptation. That means without customizing. You just get what the framework provides. But if you want to customize, you want to include your own things, then you can select at that point, different points. Okay, so different views. So this is another views where in SPC, control chart, they have different control charts. Okay, it's up to the user to select. Okay. So these are our planned in the framework. Okay. So another one is the persistent framework. Okay. So as I said, the common features are connection to databases. Framework services are connection, query, updating of databases, okay, and also retrieving. Okay, so you can update to XML, update to XML, multi-dimensional database or relational database. Okay, so this persistent framework we call XStore. Well, so in order to support users that are basically we provide API, a set of API, where they can include it into their Java program and straight away connect to either multi-dimensional database, relational database, okay, or XML. Okay, persistent, that means to save it into the database. Okay, so in order to support the non-technical users, okay, in using the system, we have built a layer up, that is the language layer, provide a language for the framework, okay, so that they can still use the framework, okay, through the language without the API, okay, hidden, the API will be hidden there. And also, we also include the enhanced locking mechanism that in multi-user transaction management, the same piece of information might be locked. Okay, locking mechanism. Okay, and then to ensure the consistency of this piece of data. Okay, And also the other one is we include a XML-based cache mechanism. This one is to speed up the performance when using the database cache, the cache memory. You know, there is a section of memory you allocate to actually retrieve your data from the server. Okay, if you still need it, it remains there, so you can just retrieve from there. Why do you use XML? Because it allows us to use it to be able to create a very big object that would with this algorithm you can have smooth navigation, because the other half of the object can remain in the cache, okay, in the cache, and the other half not needed is remain in the disk. So with this XML support, we can do that. Okay, a very big object, even bigger than the memory. Okay, it can be done. Okay. So this is the architecture of the framework. Okay, a very complex architecture. Okay. So other works are, for example, applying machine learning using cache-based reasoning. Okay, in this case we use GA, genetic algorithm, to help in retrieving the cases, similar cases, you know, framework usage cases. As an example of people have used a framework and it's saved somewhere. Okay, it's been recorded. So we use case-based reasoning to compare the cases. Okay, and then using GA to retrieve and reuse, and using pattern matching algorithm to actually adapt. Okay, so for this one, for framework documentation. And report generator is also a reusable system, okay, that allows the developer to define their report layout using XML format, including the query, to query data from the database to put in the report layout. And then the system will generate a HTML that can run on the browser. And it allows them to connect to different databases. Okay. The other one is the configurable tool for web-based courseware. I mean, basically is to be able to adapt courseware, okay, for different needs. Okay. This one is about organizational memory. Okay. So in the past, we just do, a project that we provide an ontology-based knowledge model to be able to capture the tacit knowledge of software developers, okay, when they work together. Okay, they work together by using the human metaphor, okay, memory metaphor. Okay, so it's basically for storing the software experience management. So it's for the organization. And the other one, this one is a Qubit auction protocol. It's about Qubit. Qubit is actually auction is actually the user can submit submit to the auction a secret bid, which is very confidential, highly confidential, secretive. That's not supposed to be revealed, right? So we try to, because of the confidentiality, we develop an approach where we make use of polynomial to try to distribute the bid. When the bid is submitted, which is highly confidential, in order not to let people hack, okay, we use of the polynomial to distribute the bits on top of the server. So this piece of data becomes fragmented on top of different servers. So it's very difficult to hack in that sense. And there's another algorithm to recombine all these bits when they open the auction. Okay, so when the bid is submitted, the algorithm will be launched to actually distribute the bits on top of a server. Okay, then when the auction closes, that means you can open the auction. Then the algorithm can actually recombine the bits so that you can read the whole bit. Okay, so this one is to prevent hacking. Okay, so this is one project. Okay, the second phase is actually from 2006 to 2012. So basically, it's on the topic of software quality in the architecture design, okay, as well as model change management. Okay, the research is around that, okay? Basically around that. So the first one is actually a guideline-based approach, architectural guideline-based approach for achieving non-functionality in architecture design. Quality attribute is one of the drivers in the architecture. Is one of the very important architecture driver, okay, to fulfill. Okay, we need to fulfill that driver. So, in order to fulfill the drivers, normally the architect will actually make use of the architectural guidelines to help them to fulfill the quality or non-functional quality, non-functional attributes such as performance, security, and so on. Okay. So there are already a set of guidelines in the books. Okay, but there might be new guidelines coming out. Okay, so what we do is that we at that time we collected the different guidelines. Okay, the different guidelines from different sources, books, article research, new research articles, and so on, because we want to keep the set of guidelines for reference, okay, by the architect. So architectural guidelines sometimes, other people might say design concept. Okay, it's actually the architect making use of it to fulfill the architectural drivers. Okay, so quality is one architectural driver that shape the software architecture. Okay, so we actually focus on the architecture level. Okay, some of the guidelines are, for example, architecture pattern, tactics, okay, deployment pattern, reference architecture, okay, or develop component technology. Okay, so we collected all these guidelines. We try to categorize them into different categories, and the second stage is that the problem with this guideline is that by using one guideline can give a negative effect or positive effect to another quality. Okay, to another quality. So architect has to be careful. The guideline he used shouldn't be affecting another quality. So our input is a set of prioritized quality that the architect has to fulfill, okay, to come out with the software architecture. So due to the fact that each guideline can give different effect or can affect, okay, the achievement of a quality aspects, and that is why we need to document. See what are the guidelines that can affect what quality, whether it's negative, positive, or what. Positive is good, but negative we want to remove. Okay, that negative guideline, that guideline that affect certain quality in the prioritized list of quality attribute, we have to remove them, even though it can be used. Okay, but not only a guideline can affect the quality, even the guideline also can give some effect to another guideline. It can conflict with another guideline. Okay, it can overlap with another guideline. Okay, it can complement. Of course, we want the complement. If it can complement with another guideline, then that is good. Okay, so we actually document all this out. Okay, the relationship, and then we build the rules, the algorithm. Okay, to look into, okay, how to remove some guideline if it gives a negative effect to quality, or it gives, especially it gives negative effect to a high prioritized quality. okay, or it conflicts with another guideline used by that guideline is supposed to have to achieve some quality. Okay, so we have to build the rule in order to avoid having conflicting or negative guideline affecting other quality. Okay, so after we have collected all these things, we can build a tool. So we managed to build a tool that can help architects when they designing software architecture. Okay, so that based on the set of quality, prioritized quality, they can straight away get a set of guidelines, non-conflicting, no negative effect to each other. Okay, then they can look at each guideline, so whether this guideline giving what effect to what quality, and so on, right? So this tool will be a supporting tool for the architect. They do not need to go and manually search, okay, to document all these things. So the research is on studying of the effect and studying of the overlapping guidelines, okay. So the tool is built for them to, speed up, okay, to look at the guideline, okay. So from the guideline, it could be a certain architecture pattern. Each pattern is actually recommending a solution to a recurring problem. Pattern is also reusable, okay. Pattern is reusable, but it recommends a solution. But the problem of pattern is that it recommends a solution descriptively, or either give a structure, okay, but not the behavioral part, okay. So we can retrieve the structure for the architect to see, okay, straight away. So these are some of the screenshot of the tool, okay. Okay, so that was the tool to help the architect. This one is about the design pattern. Design pattern is actually a reasonable concept also that software developer can apply to help in their design problem. So it recommends a set of solution to a set of recurring problem, the same problem happening again during design. Okay, so what is the thing is that design pattern normally capture all these problem and all these solution narratively. I mean, just describe. It also support the structure of the solution, so the architect can use. But what is lacking is the behavioral part. There is very little behavioral part, okay, supported by design pattern. Each design pattern has a different structure and behavior, but the behavioral part is not mentioned at all. So that is why it's very difficult for the designer to make use of design pattern. Okay, so what we want here now is to augment the functionality of design pattern, or to actually extend the functionality of design pattern by extending from UML profile. So we create a profile. Okay, we want to include interaction behavior, interaction variance, interaction behavior between the different participants of the pattern. Okay, and interaction roles in the design pattern. To do that, okay, we want to also provide options for them to choose. Not only the interaction behavior, but we want to provide alternative behavior so that they can choose. Okay. What we need to do is to create a profile, UML profile. Now, UML is a de facto standard language. It has a set of spec. Okay, the spec actually define the meta. What do you call it? Meta model for the concept. Okay, so it has a class. It has some of these classes. Okay, sorry. Okay, that they call as meta class. So, for example, a sequence diagram has a set of meta classes that describe about sequence diagram. Okay, so for this case, we want to extend the sequence diagram to include alternative behavior. Okay, then we extend from UML, we create a profile, we include all the meta case related to sequence diagram. Then we will extend from this from the meta class of the sequence diagram to create stereotype. Okay, stereotype is another concept in UML. Okay, and so that will allow the designer to define and visualize, okay, the interaction behavior, okay, of the pattern. Okay, because what is lacking is interaction behavior. So this is how we do it. We create a profile. Okay. Then we include only the meta class related to sequence diagram. So interaction use, if you go to UML spec, you can see interaction use is there. Interaction, message, lifeline. Okay. So we want to extend. So we extend. These are our stereotype. We define stereotype. Okay. So these are all UML and UML spec. We extend from this meta class of UML, and these are all our stereotype. We extend this stereotype so that we can extend the functionality for the interaction behavior. Okay. In this case, we only try out for one pattern. Okay, that is observer design pattern. Okay, observer design pattern, it has the participant, pattern participants such as observer as well as subject. Okay, this is to allow to reflect the changes of a subject. Okay, if there's any changes on the subject, the dependent object or the observer can be reflected. So what the observer needs is to subscribe to the subject. Okay, so this will allow the subscribe to be done. Okay, subscribe or remove the subscribe. Okay, so we want to extend from interaction, the interaction. Okay, if you see UML, there is this interaction operator called ref. Right, ref. So we want to extend functionality on it. So we extend. Okay, extend. Okay, so these are the things that we want to include. Okay, of course we also want the message and lifeline. Okay, okay. Fragment type is there are two. One, this is an enumeration type. One is called variant. The other one is unique. So if you want to provide variable or alternative behavior, we use variant. Okay, otherwise it's unique. Okay, so this is the description of pattern on observer design pattern. So it has a structure, as you see, but there's no behavior part. So this is for to model one-to-many dependency between objects, so that when one object changes state, the rest of the dependent object should be notified to reflect the changes. Okay. So we once we have defined the UML profile, we can create all this. You can see this ref. This is actually the interaction, okay, in sequence diagram. So we have included all this. Okay, this is for the observer to attach, to subscribe to the subject. Okay, this is to remove the subject, and these are the two variant alternative behavior. So we want to provide the behavior of pull and push. That means you want to notify, okay, the subject will notify the observer either through pull method. Pull method, that means, do method means it just notify. Then the observer will need to come and get the data to reflect the changes. Push method, that means the subject will push the data, that means send the data to it without notification. Push the data to the observer, okay, to get the changes, to reflect the changes. Okay. So if you can see, okay, this one, with this you can automate this. Okay, this is the one line is a push. Okay, pull method, you have one notification, the other one is come and get the data. Okay, so these two pieces of interaction behavior, the developer can actually choose either one that they want. Okay, okay, this one is to support interaction behavior for the observer, for this thing. So if they want to adapt to their user-defined name, it can be substituted. It can be substituted, okay? Like this one, auctioneer, auction. Okay, in the case of auctioneer, and this one is a bidder. Okay, you can substitute. Okay, so this one is about the increasing or augmenting the interaction behavior for design pattern. Okay. Okay, the other one is on the change management. Change management, that means actually in UML, if there is a change, if there is a change in one model diagram, there is some change in one diagram, okay? In certain cases, there should be some change also in another diagram. But this is not reflected in the tool, in the visual paradigm, okay? So now we want to make sure that this change should be done, okay? So we develop Coevolution Framework, okay, to actually preserve all these changes. If there is a change, for example, if you add a sequence, in a sequence cycle, you add a message to an object. The receiving object, okay, the class of the receiving object should create that message in the class. But this is not done, okay? So this will lead to inconsistency. So we want to preserve all this link. If I change the sequence diagram, okay, my class diagram need to be changed. If I change my sequence diagram, maybe my state diagram need to be changed. Okay, so we define all these links, okay, using the pattern, using coevolution pattern. So for this framework, it supports my 80 pattern. Okay, just for the link, different link. Because we consider five types of diagram. Okay, and then also supported by 45 templates. Okay, the templates will be able to effect the change, help to effect the change. Okay, and will help to determine the impact, and for impact analysis. Okay, traceability analysis, so that the changes can be seen. Okay, before the change, and then for each type of change, it's different for different diagram. So we also use a template to define each type of change. A change can be a delete, create, and so on. Okay, basically it is like that. Okay, I don't want to go deeper. So different type of diagrams, and these are the patterns, about 80 patterns. Okay, we because UML lacking in formal aspects, so we have to make use of battery nets. Battery nets is a formal language. Then we combine these two characteristics into an object-oriented battery nets, okay, to take advantage of the structural property of UML with the formal capability of battery nets. Okay, so each change is also defined in the template. Okay, so this is basically for change management. Okay, the other one is we also formulate a set of object-oriented metrics as an early indicators of faulty classes and components. This is for software quality. And that we can actually develop as a plugin in Eclipse. Eclipse is an IDE tool for software developer to develop their Java program and so on. So if the metrics developed as a plugin, they can check the quality of their source code. Okay, in terms of class-based cohesion, component-based cohesion, okay, class-based inheritance hierarchy, and so on. Of course, there is a set of metrics already available. So what we develop all these are not available at that time. Okay, cohesion is to measure how cohesive a class is. Okay, how meaningful is the description of the class, such as the method and the attributes, to the meaning of the class, to the semantic of the class. Okay, it's actually measuring something like that. Okay, so component base is actually on a set of component. A component we have a set of classes. Okay, so all these are developed as a plugin in Eclipse. Okay, so that developer can check while they develop their software. Okay, the source code. Okay, so the other, projects are smaller scale, such as workload performance. This is for database tuning. Okay, to look at the workload performance of individual database user, and the data administrator can tune. Okay, they can tune tune in real time if there's a bottleneck. Basically, this one will actually display the memory, the memory part, okay, of the database administrator. So the database administrator can tune, can maybe, if they see a bottleneck there, either give back more space, okay, give more memory space, or reduce, okay. So this one is to exploit the data mining tool by developing a framework so that user can connect to the different data mining tools. This one is to exploit the multi-core architecture of a certain PC by dividing the workload, by developing a problem into different workload, and then to run concurrently by the core by using work stealing technique. Okay, so I think I want to end a little bit faster. This is the last phase. Okay, so the third phase of my research landscape is basically related, developed from 2013 to now. Okay, this is mainly to software maintenance and testing. Okay, for example, clustering of software system to actually derive a high-level representation of a software design. Okay, so that it's easier to perform maintenance. This is especially for poorly designed software system, without documentation, okay, without architecture, nothing. Okay, and the other one is the traceability of change request. It's actually to develop a way, okay, from the developer submitting a change request, how to trace it to a set of source code files, okay, relevant to the features defined in the change request, so that it provides an easy way for the developer to know where to go for changes. Okay. Okay, that's the reduction for software testing. We focus on model-based testing, sequence diagram. Okay, this one is the purpose is to be able to derive a set of optimal set of test cases, highly diverse set of cases with no duplication. Okay, so that it can reduce the testing cost. Okay. So all these projects, it needs to apply techniques such as, the data mining, AI, and also machine learning. Okay. So some of these main tasks are mining data from software repositories, source code or GitHub. Okay. Then representation of a big structure. Okay, this is basically for a big project. Okay, a very big project. It's very difficult to use UML, okay, so on, just to see the overall or to analyze, okay. Okay, we make use of the complex framework for analysis using graph theory metrics to analyze pattern, okay, or sometimes we use reverse engineering just to reverse engineer from the source code, okay, and then we apply the dedicated techniques based on the problems that we want to solve. And we apply different data mining, emerging techniques such as AI, and machine learning. Okay, this one, the clustering. Okay, clustering of the software to give a high-level view or high-level representation of a software design is to solve the architectural recovery problem. Okay, to recover a high-level view of a poorly designed software, so that you still can salvage something for the maintainers to facilitate their maintenance. Okay? If let's say a software, a set of program poorly designed, okay, of course we also want to look at the high-level view. Okay, so we actually develop and enhance clustering, making use of the dendrogram cutting technique. Okay, we enhance the existing clustering technique, okay, by minimizing redundant effort, because during clustering, the existing technique did not address that redundant effort, okay, to speed up the clustering, and also penalizing for the formation of singleton cluster. Sometimes the clustering producing a cluster that has a single entity, which is actually not valid, but also for the existing technique, they do not consider detecting all these things. So we want to prevent all these things. Okay. So the steps are that we actually identify, okay, clusters and relationship. Okay, and then we calculate the similarity of the relationship between the classes. Okay, after that, based on the similarity, we put up all these relationship into a dendrogram. Dendrogram is like a tree structure, a taxonomy of tree structure. Okay, it's actually to build a cluster hierarchy. Okay, and then we apply it. After that, we have to cut. Okay, we want to produce the best cut. That actually based on the least square regression technique. Okay, least square regression, cutting based on that, okay, to produce optimal cluster. Okay, right. So you can see very huge system. You will see there are a lot of clusters. Okay, when you reverse engineer, you tend to see like that. Okay, it's very difficult to analyze. Okay, so what we need to do, we calculate, the similarity between the relationship between the classes, identify the relationship, calculate the similarity, and then put it into a dendrogram. These are the dendrogram. You have the software entity here, then if they have relationship, we join them together and so on. Then after that, we apply the clustering, cutting the dendrogram. At the cut, the best cut, we have to determine where is the best cut. The best cut based on least square regression technique. The best cut that can produce maximize cohesion, minimize cluster, minimize coupling. Okay, that is a very good practice of software engineering. At a different life cycle, we have to ensure this is maximized when you develop any model or what. We have to ensure maximize cohesion within the classes or subsystem, but minimizing the coupling, because coupling will actually lead to dependency. Okay, that is not good. Okay, so using the algorithm, we can know the best cut. Okay, we can determine the best cut. Okay, that produce the clusters without a singleton. That means cluster with only one entity, and removing the redundant effort. Okay, not exhaustive cutting. We don't do exhaustive cutting. Okay, some of the existing systems, they use exhaustive cutting. Okay, so we actually can know where to cut to get the maximum cluster. So we compare with the gold standard. Okay, the gold standard are actually in dotted line. So ours cluster are actually in blue line. So we can compare, we get 90% accuracy. Okay, 90% accuracy. So this is one, clustering. So the second project, the clustering is, we want to use semi-supervised clustering. just now you see that one, the first one is actually unsupervised. Okay, the whole process is actually automated. Okay, we don't say that how many cluster we want. Okay, it's actually automatic. It depends on the cluster to produce how many clusters. Okay, so this one is actually semi-clustering, semi-supervised. Okay, in the sense that we want to provide expert knowledge. Okay, we want to the minimal supervision of expert knowledge, or even site knowledge. Okay, so we want to facilitate the work of expert. Okay, by representing all this software into complex network, so that it's easier for them to identify the clustering constraint. Okay, clustering constraint is actually put in the form of must link and must not link. We know which part could be classified as must link and which part shouldn't be linked. Okay, the same thing is for poorly designed software, but this one will improve the clustering result. Okay, so the step is like that. The same thing we mine from the repository, source code. Okay, identify. Okay, extract the class diagram, and then now we calculate the complexity between the classes relationship, complexity of relationship and the classes. From the complexity of classes, we can know the relationship complexity. Okay, then with the complexity and so on, we put it into a complex network. We transform it into a complex network. That means the whole thing is converted into complex network, where the nodes are actually the classes, and then the relationship are actually the arcs of the classes. In the arcs of the nodes, we actually put the weight, because we have to calculate the weights for the complexity. So we have a new formulation to calculate the weight. Okay, so to know what to cluster or not to cluster, you have to based on the weight also. Okay, so converting into a complex network. A normal complex network, the arcs without weight. Okay, so we supplement it with the weights. Okay, so that it gives more information. So that is why we call our network as weighted complex network. Okay, and then we apply graph theory metrics. Okay, on a complex network, such as clustering coefficient. Where is the hub? A hub is where you can identify the pattern called hub. Is where you have a lot of interaction. Okay, interaction in degree and out degree, or very heavy average degree. Okay, and then we also can identify the cliques. Cliques will be very even heavier. Okay, you have the neighbor of the hub. Neighbor of a hub. So, okay, neighbors are the classes. Okay, they are also neighbors among themselves. So you can see this is a very dense, okay, classes. So based on graph theory metrics, we identify our clustering constraint. Okay, and then we will put all this structure, all this clustering constraint into a dendrogram. Okay, dendrogram. So from there we cut. Okay, using the previous algorithm we cut. Also the same, based on the least square regression method. So the purpose is to be able to derive a set of optimized clusters. Okay, that will maximize cohesion, minimize coupling. Okay, so this is what we do: mining, then calculating complexity. Okay, then and then represent into the complex network. Then identify patterns such as hub, click, and so on. And from there we derive the constraint. From the constraint we build the dendrogram. Then we apply the cutting. Okay, and then we get the clusters. Okay. So this is a complex network. If a very big project, you will have this. So using UML is not possible to analyze. Okay. On top of that, we build with the weights so that it can help us to analyze easier. Okay. So you can see some spots, very dense, okay? So we put everything in the dendrogram, so you can see a dendrogram become very complex for a big system, okay? Then this is a best cut, maybe here. Best cut that based on least square method, least square regression method, then maximize cohesion, minimize coupling. So the same thing, we didn't determine, okay, we didn't say how many clusters we want, okay? It depends on the algorithm to derive the cluster, okay, before the clustering, okay? Okay, this one is on the traceability of the change request. Okay, sometimes, especially during maintenance, change need to be done, okay, because things are changing. So there are features mentioned in the change request. So based on the features of the change request, we want to trace it to the source code, a set of source code that is related to these features. Okay, this is to speed up the work of maintainers also, okay, to help them to identify the set of source code to be changed. So the same thing we mine from the repository. We mine from software issue tracking system, okay, version control system, bug tracking system, okay. We mine, then we actually get the now information related to the software features in the change request, find it from the change commit, comment of the commits, commit logs, developer profiles and so on. And there we identify two mechanisms for weighting the term, give weights to the term to see how related they are to the features. For this term weighting, we look into two aspects. One from the aspects of time. Okay, it is said that the most recently changed data is actually the cause of future bugs. So we want to give that more weight. Okay, so also we another aspect we look into is actually the developer. From the aspects of the developer, a certain piece of data has been changed. If there are many developers changing the data, so it can also be the source of bugs, okay, for future bugs, okay. And then we then do the ranking, finding you see where this total weight of the now from the source code, okay, the higher they are, the higher ranking they are. So from there we retrieve the first 5 to 10 source code files, okay. So the whole thing is like that. These are the change requests. This issue tracking system is actually storing all those change requests, previously fixed requests. Okay, previously fixed requests. And then version control system are basically the versions of source code. Okay, so we do all the term weighting, collecting from the repository, mining from there, then weighting of terms, and then retrieving. Okay, so and then the next project is on the test suite reduction. Test suite reduction, that means how to get a set of test suite, reduced test suite, but not only reduced, but it's highly diverse, with highly diverse test cases. The most optimum that can cover for the test of the sequence diagram. So we focus on model-based sequence diagram. Model-based testing, normally they generate test cases by using some exhaustively, by using some coverage criteria, and that will result in generating a set of duplicated test cases. So that is how we want to remove the duplicated test cases. Okay, so this algorithm is actually supported by 3 components. One is a test to optimization model that actually defines the sample size and also the fitness function. Okay, fitness function, of course, we want to find the optimal solution based on the set of candidate solution. Okay, so another second part is on the test case selection mechanism. This set case selection mechanism will perform the function of selecting the test cases that are diverse enough based on the similarity, calculation of the similarity function, supported by test reduction, redundant measurement metrics. We include 6 set-based and 2 sequence-based similarity function to help to calculating similarity. Okay. And then we make use of the meta-heuristic algorithm for the search. Okay, to search for the most diverse. Okay. Okay. Okay, these are the one. Okay, you have the sample size and the test suit. Okay, outcome of it, you get a reduced test suit. So a reduced set of test suit will actually save the execution cost, okay, of testing. Okay, this is the last slide. Okay. So, okay. Okay, another one is approach to integrate prioritization of functional and non-functional. Existing solution is to prioritize functional and non-functional separately. So in this project, we want to integrate the process of prioritization together. But we still produce a to-list. What they want is the to-list. Okay? But we take into consideration because non-functional also influence functional. Functional also influence non-functional. You cannot separate them. Okay? You have to be integrated. Okay? So this is about complex network also. We make use of complex network actually to analyze maintainability and reliability of a big software system. Okay? And this one is about pattern detection. So this is to detect whether the piece of a set of source code using a certain pattern, and also and the trace the quality of this pattern. Okay, for source code localization, of course. Okay, to based on some bugs in the source code, you will facilitate for deriving a set of source code location. Okay, that will be the source of the bugs. Okay. Okay, so the rest not so important. Okay, so I think that's all. Too long. Okay, thank you.
Thank you, Professor Lisa Peck. Ladies and gentlemen, now I would like to invite Professor Dr. Shaliza Ibrahim to conclude the lecture which has been delivered by Professor Lisa Peck a moment ago.
Thank you. Thank you, Professor Dr. Lee Sai Peck, for a most interesting and insightful lecture. And like in many fields of research, research in software engineering, or SE, is impacted by the prevalence of revolutionary techniques and technologies originated from emerging fields due to their popularity and potential. The emergence of the range of advanced techniques and sophisticated technologies in big data, data mining, machine learning, and artificial intelligence have given a boost to various areas of software engineering research, as it has enabled software engineering researchers to apply, harness, and leverage these techniques and technologies in their research and development for achieving optimized solutions to some SE problems and challenges that are otherwise not as effective using only traditional software engineering techniques. Prof. Lee's lecture today talks about the research landscape and experience based on her 25 years of experience as an academic at the University of Malaya. Professor Lee has highlighted a variety of SE research studies that has been conducted at the Requirements, Architecture and Reusability Engineering Lab, ranging from object-oriented modeling, requirements and design engineering to software reuse and maintainability issues, with a focus progressively shifting from using purely software engineering approaches to leveraging on some of the more efficient and intelligent techniques in big data mining, machine learning, and artificial intelligence. I believe from Prof. Lee's inaugural lecture today, we can see that this research has significantly contributed to the SE research community and will be paving new software engineering research on innovating capable software system in the future. With that, join me again to congratulate Professor Lee Peck for this excellent inaugural lecture. Thank you.
Thank you, Professor Dr. Shaliza Ibrahim, for chairing this lecture. I would like to take this opportunity to thank the management of Faculty of Computer Science and Information Technology, University of Malaya, distinguished guests, as well as all who are here today for your time. With this, we have reached the end of the lecture. On behalf of the University of Malaya, I would like to apologize if there had been any shortcomings from our side in organizing this event. Refreshment will be served next door at the foyer of Block A. But before that, I would like to invite Prof. Shaliza and the management of FCSIT to the stage for a photo session with Prof. Lee. Ladies and gentlemen, once again, thank you and have a pleasant afternoon.